Hi, welcome to a new lecture. Today is an introduction to autoencoders. So we'll be trying to understand the intuition behind autoencoder, and also we will code an autoencoder completely from scratch. So there are two purposes to me recording this video. One is with an intention to keep this as a standalone video. So even if you are watching this lecture without any context, you will understand most of the important aspects about autoencoder if you are interested in the concept behind autoencoder. But I'm also planning to keep this lecture as part of an ongoing series called Transformers for Vision, in which the next topic that we are planning to cover is transformers for generative models, like using transformer for generating images like stable diffusion. But before going into stable diffusion, we need to talk a little bit about diffusion models. Before talking about diffusion models, we need to talk a little bit about variational autoencoders. And before talking about variational autoencoders, we have to talk about autoencoders. So that is the second context in which I am creating this lecture. Either way, if you have followed the transformers for vision at all, or you are watching this video as a completely separate lecture video, both of that will work for you. You will enjoy the lecture and you will at the end of the day understand what exactly is this famous architecture, what are its uses, what are the challenges of the vanilla autoencoder architecture, and how can you code one from scratch to sort of create your own images. This is not the greatest of generative AI models, and I think many people know that, but I think the exercise of constructing an autoencoder from scratch will give you a great intuition about latent space, about some ideas behind probability, etc. So let's get into the lecture. The basic architecture of autoencoder looks like this. There is an encoder, there is a decoder, and in between there is something called as the latent space. So whenever you see this kind of trapezoid shape with width decreasing, you can imagine that to be a representation of compression going on. You will see this even in convolution operation when your spatial dimension is shrinking. So in encoder, the information that you provide at the input, the information can be an image of certain number of pixels. That information will get compressed to be represented in a lower dimensional space. And this space is called as latent space. And decoder, what it does is it tries to reconstruct the input that you have provided here. So if the input is an image, decoder will try to reconstruct the input just by looking at this compressed version of the same input. So the compressed version of the input lives in this latent space, which is a much more lower dimensional space. And with that, decoder will try to perform reconstruction. Let's try to understand this with a concrete example. So if we consider the MNIST handwritten image as the input, the data is the image itself. And this image, when we are passing it into an encoder, this image by default has 28 by 28 pixels. It's black and white. So you can consider the input data, which is this image, to be living in a 28 by 28, which is 784 dimensional space. How do you get 784? Those are every single individual pixel. So each pixel value you can consider to be residing along one separate dimension. An encoder, what it does is, we can look at the detailed architecture of the encoder in a little bit, but in short, what it does is it compresses this 784 dimensional data into, let's say, 64 dimensional data. So of course, there will be some losses happening during compression. So when you are inputting this image is taking 784 dimensions to represent it fully. But when you are compressing it to 64 dimensional space, some information, hopefully some useless information, is discarded, and some useful information, which is the most critical for reconstructing the image, is retained in this latent space. And when you perform reconstruction, you are again trying to reconstruct back a 784 dimensional version of the input image. But this time when you are doing it, you don't have access to the input image. You are only accessing the 64 dimensional latent space. So this is a great tool, right? If you can train such a network, this is essentially a neural network. If you can train it, it acts as a very good compression engine. And how do you train this? You train it by constructing a very simple kind of loss. What is the loss? Loss is basically how bad your reconstruction is compared to your input data. The easiest way to compare this is just do a mean squared error MSE, where mean squared error equal to 1 divided by 784. You have 784 pixels, and let's say the input data is PI data. So this is the ith pixel from the input data minus pixel value from the input data, P reconstruction or PI reconstruction So this is the difference in pixel value between data and reconstruction. You square it and you sum it over I, where I runs from 1 to 784. So you perform a pixel-wise comparison between data and reconstruction, and that is the mean squared error. If this mean squared error can be minimized, it means your reconstruction will look very similar to your input data. What happens if the mean squared error is 0? It means every pixel is perfectly matching. Every pixel in the reconstruction is perfectly matching with the data. This is the idea behind autoencoder. Now, if you have a trained autoencoder, you can just take the encoder part of it. You can ignore the decoder. So if you ignore this part, your encoder part of it will act as a very nice compression engine. It can perform very efficient compression of your 784 dimensional input into 64 dimensions. This 64 is not a fixed number, by the way. We can define whatever, and in today's coding we will try to pick 64, 12, 2 dimensions, 1 dimension, 3 dimension. We can try all of those. So if you just consider the trained encoder from a trained autoencoder, that encoder part will act as a very nice compression engine. And the trained decoder will be good at converting your compressed version of the data into reconstructed version. Of course, there are some challenges here. We will discuss that soon. So the compressed space will basically look like a n-dimensional space where there will be vectors, right? So this data you can consider as a vector. So originally it is 28 by 28. If you flatten it, it will look like a 784 dimensional vector, which will have something like this, one column where the dimension is 784 multiplied by 1, right? And each dimension will be the value of each pixel. And when you reach the latent representation, the lower dimensional space can be something like 64 by 1, right? So this diagram is just showing the compressed latent space. And this latent space is where all your input data will reside after being encoded. So now there is a challenge. Let's say I want to now generate a new image. If you were to consider autoencoder as an image generation model, you can sample a random point from your latent space, right? And you can hope that if the decoder is a trained model, if the decoder part of the autoencoder is trained, if you pick a random point from your latent space, that point can be decoded or reconstructed into an image. So in this case, you are hoping that the sample data point from your latent space, when you are passing it through decoder, it can be reconstructed into one of the MNIST type of images, right? That's what your hope is. But actually it doesn't happen. If you sample from the latent space randomly, what in reality happens is a messy reconstruction. The reason for this is that autoencoder is learning to represent every single image into one single point in the latent space. So even if you are sampling from the same latent space, the sampled data point may not correspond to any meaningful image. So when you are trying to reconstruct an image using your sampled data point, using a trained decoder, you may end up getting a messy image like this, which does not look anything like a MNIST image. One solution to this, which you may think, is how about this? How about we take a reference point and we sample near the reference point? What is a reference point? A reference point is something like this. I input a data. So let's say input data is this handwritten digit 5, and this is a trained encoder. Okay. So I use the trained encoder to convert my data point into this. So this is in the latent space. So this is, I'm just drawing it in 2 dimensions because that is the best I can do. But imagine that latent space can be 2 or 3 or any number of dimensions. So this is the latent space. And in this latent space, now we know that this data point directly corresponds to this image. So if we were to pick this data point, we might get a very closely looking reconstruction similar to this digit 5, because we have trained the autoencoder on this data set. So then our thought is, okay, but then what if we pick a point which is very nearby this reference? So what if we pick this green point? So green point is a new point in our latent space, which is very close to this reference point. So the red point is reference point. Why am I calling it as a reference point? Because that point was constructed directly from an input image. Input image was passed through a trained encoder to produce that point in the latent space. We sample a point very close to that reference point, and then we might hope that this reference point, because it's so close to the sample point is so close to the reference point, hopefully if we pass it through a trained decoder, it may construct an image which may look like this handwritten digit 5, right? That is what we are hoping. But in autoencoder, that does not happen. In autoencoder, even if the sample point is very close to a reference, it results in a messy image reconstruction. There are many reasons for this. We can actually do some experiments today in the code. But the main reason for this is that autoencoder actually is mapping an image into one single point. So if I have a handwritten digit of 5, it is being mapped into this point. If I had a handwritten digit of, let's say, 6, or another type of handwritten 5, like this, if I had an image that looks like this, maybe it will get encoded into a point in the latent space that looks like this. Now there is no guarantee that something in between. So this is handwritten digit 5, this is handwritten digit 5, but there is no guarantee that a point in between might also be a latent representation of a handwritten digit 5. There is no guarantee like that. So if you sample any point randomly, or even if you sample a point close to a reference point, it does not necessarily mean that decoder can convert it or reconstruct it into a meaningful image. This is the reason why variational autoencoder was introduced, but in this specific video, I'm not going to cover variational autoencoder. I'm planning to cover it in a separate video. But today let's focus on what autoencoder can do and what it cannot do. And if we were to train it from scratch, what does the architecture look like? So these are the things which we are going to do. So I have created a diagram here, which I want to, to have you make a quick walkthrough through this diagram. So this diagram is showing the sort of the architecture of autoencoder that we are going to build today. Some details are missing, but I'll show you another version of the diagram with more details. So you have an input image, which is 784 pixels. So you are in the first step flattening the image. So 28 by 28 is flattened into 784. Then of course there will be activation function, which I am not showing here. Then this 784 dimensional representation will be compressed into 256 dimensional representation, and 256 dimensional representation will be further compressed into whatever is the latent dimension. And this will be a variable. We can define the latent dimension as 64 or whatever. In fact, this 256 is also our choice. We can pick whatever number we want in this hidden dimension. So this is the input dimension. This is the hidden dimension. And this is the latent representation or latent dimension. And then once we have the latent dimension or latent embedding, we again expand it back through a hidden dimension of 256. We expand it back into 784 dimensions, and this we can kind of plot like this. And of course there are activation functions in between. Now what we are going to do is, today we are going to run the code, first write the code and then run the code with latent dimension 1, latent dimension 2. We can also run for latent dimension 3 and higher dimensions. And we can try to construct the images corresponding to originals. So these are the original images 8, 1, 8, 3. And when you reconstruct, we can see what can be done. So here the number of epochs which I ran for is just 5. But we can see if we run more number of epochs, whether our reconstruction look better. Here you can see that if the latent dimension is just 1, every image is getting represented by one number, right? It's just a one-dimensional parameter. Then of course the reconstruction is not very good. And as you go from 1 to 2 to 3, the reconstruction is becoming better, but although it's a bit blurry or messy. See, here 9 is getting reconstructed into something confusing. You can't say whether it's a 9 or 3 or 5, right? This reconstruction. And here what I'm plotting is the latent space itself. Because 1D latent space has only one dimension, we can easily plot it. So you can see that there is some grouping. Different digits are grouped in a histogram to different latent values. So a digit like this one, a digit 1 is being represented using a latent value whose average is close to 0.5 or something. A digit like what is this pink color? Pink is 6. A digit like 6 is represented using a latent value whose average seems to be like 2.7 or something like that. And if it's a 2D latent space, we can directly plot as a scatter plot in 2 dimensions. And you can see that there are very nice clusters emerging basically. So this is one cluster where all the data points corresponding to digit 0 is living. These red clusters are those data points corresponding to 3 and so on. In 3D space also such clusters emerge, but it will have 3 dimensions to spread. And in more dimensional latent space, we cannot directly plot, but we could do something like principal component analysis to boil the plot of the latent space into 2 dimensions or 1 dimensions, and we can still plot it. So this is what we are going to do. And the architecture that we will use is something which I showed you above, but the only thing which I did not explain is the activation function. So we will have a ReLU activation function, and these are all fully connected nodes, by the way. So if there are 784 nodes here, after each node there will be ReLU activation, and they will be fully connected to the 256 nodes in this layer. I could not draw that many connections, so I just skipped drawing it, but just, you know, all the layers are fully connected to each other. I mean all the consecutive layers. And then after this 256 node hidden layer, you will have ReLU activation after every node, and then you connect to the latent dimension. Again, it's fully connected. So latent dimension has 64 or 32 or variable number of dimensions, and then back. So this is the encoder, and the decoder basically constructs back from latent dimension something to 256, and then there will be ReLU activation. Following that, you project to 784 dimension, and following that there is sigmoid activation, and then you have the final reconstructed image. And the loss will be mean squared error loss, MSE, which will compare pixel by pixel between the input image and reconstructed image. So this is in a nutshell what we are going to code. And now we can directly go ahead and try to construct this autoencoder in Python. So you can open a Google Colab notebook. This is going to be relatively easy code. So coding autoencoder from scratch. And runtime, you can connect to any available runtime that you have. I have a Google Colab Pro subscription, so I can connect to V6 TPU, but you can also connect to whichever GPU or CPU or TPU, because the code is not that complex. So it probably would not matter too much which runtime you're using. So first we are going to import libraries that are needed. So first is import torch, which is PyTorch. Import torch.nn as nn. We will need this for inheriting certain properties when we are defining our neural network. So from nn.module, we will inherit certain properties for our class that we will write. Then import torch.optim as optim. And from torch vision, import datasets. So this is for getting MNIST or fashion MNIST. So fashion MNIST dataset, you might know this is the dataset. There are different classes of these clothings, and you can try to reconstruct these images also. So we can try both MNIST as well as fashion MNIST in today's coding, and transforms for performing transformations on the input image. Then from torch.utils.data, import data loader for loading data into different batches, and from import matplotlib.pyplot as PLT. So, and I have imported NumPy also here as per Gemini's suggestion, but I don't think we really need NumPy. We'll see if we need it, we can import it later. Let me delete it for now. This matplotlib is for plotting the generated images. So these are the only libraries. So once this is done, you can just run this. Next is defining the device. So device equal to torch.device. This is standard. Okay, if CUDA is available, use it. Otherwise use CPU. So I just accepted Gemini's suggestion here. So I'm just going ahead with it. Next is the data loading, data into train and val. So first we can define a variable for batch size. So batch size is the number of images per batch. We can keep it 64 or 128 or anything that we wish. I'll keep it 128 for now, and change it later if needed. Then the transformation that we need to apply, transforms dot compose, compose with C capital. And the only data transformation that we are doing here is to convert the Python image library format data into tensor format. We need tensor format image to be fed into the neural network. So transforms dot to tensor. That's the only transformation. We are not necessarily scaling it based on mean or standard deviation. We can do it, but right now we don't have to do it. Then train underscore dataset. Anyway, we are planning to reconstruct the original image, right? So it's not a multi-class classification problem or anything. So train dataset equal to datasets. So this is where we define whether we want to use MNIST or fashion MNIST. We can start with MNIST, and root equal to dot/data. Then this is the folder in which data will be downloaded to. Then train equal to true. Then transform equal to, we can just paste it. So just to avoid confusion, I can just write this as data underscore transform, and then I can pass that here. Otherwise, if I use the word transform, the variable name transform, you may get confused. So transform equal to data underscore transform, download equal to true. Then this is for train dataset. Now for validation dataset, actually there is no validation that we need to do here. We just need to see if the trained autoencoder is creating good enough images. So we don't have to necessarily do validation here. So we can just say train loader. This is the data loader part. Train loader equal to data loader, where we have to mention the data set is the train data set. This is where the data points are coming from. What should be the batch size? Batch underscore size is equal to, so here again, to remove confusion, I'll just put this in capital letters, batch underscore size. So we are passing that variable here, and shuffle equal to true. We can just shuffle the batch data, and that's it. So we now have the data set in batches of size 128, and each individual data point will be a tensor. It won't look like an image. It will be in a tensor format, loaded using data loader into this variable train loader. And once this is done, you can just run this piece of code. So now data is being downloaded and train loader is ready. Now we have to write the class that defines autoencoder. So class autoencoder, and into this we pass nn.module so that autoencoder can inherit bunch of properties written inside nn.module. This is the standard argument that is passed into any class which we build in Python if we want to use the predefined libraries in PyTorch, where various properties of gradient descent, etc. are defined for neural networks. Then we say define underscore init. This is the init constructor for initializing the current object, and into the init constructor we may have to pass a few arguments, but self is the only argument that we need to pass by default. The rest of the arguments we will figure out if we need to pass or not. Then so this is the init constructor for the current object belonging corresponding to autoencoder class, but there is such an init constructor in our parent class also, which is in nn.module. So then we say super means we are now referring to the init constructor in the parent class, super dot underscore init underscore. So this will initialize the init constructor in the parent class also. Then we first define the encoder part, then we have to define the decoder part, and then we have to define the forward pass. So then we can say define forward and here self comma x, where x is the input. So we have to write the encoder, we have to write the decoder, so that irrespective of which loop of forward pass we are in, that is the encoder we are using and that's the decoder we are using. And then in forward pass we do we pass the variable from one layer to the next. So first let's write encoder. Encoder is first the input image comes, so self dot encoder equal to, and this encoder is bunch of layers, right? So you can use nn dot sequential to connect those layers. So what is the first layer? In the first layer you have a fully connected network, so it's a linear connection going from 784 dimensions to, let's say, 256 dimensions. So 256 is now the hidden dimension, and following this there is a ReLU activation. Following this, the hidden dimension is projected into our latent dimension. This is where I can define a variable called latent underscore dim, and I can pass it here. So self comma latent dim equal to, let's say, 32 or something. So the latent space has a dimensionality of 32. And then again, after that, nn dot ReLU. So after projecting into latent dimension, we apply ReLU activation. Then I don't think in the figure I showed this explicitly. Just let me. So after projecting from 784 to 256, there is a ReLU activation. So this part is actually wrong, my bad. I have drawn this ReLU in the wrong place. After projecting from 784 to 256, you have a ReLU. After projecting from 256 to 64 or whatever the latent dimension is, there is another ReLU over here. Okay. So please note, in this image, we don't need a ReLU activation here because there has been no operation. So the only operation happened so far is flatten. So after flattened, vector that is 784 dimension, after it is projected into 256, only then we need the activation. So this is technically not needed, but we will need an activation right after projecting into latent dimension. So two ReLUs, one ReLU after 256 dimension hidden layer, another ReLU after projecting into latent dimension. So this is the first ReLU, this is the second ReLU. That's it. So that is the encoder. Very simple, right? And decoder is self.decoder equal to, again, nn.sequential. This part is easy. You can already guess what we are going to do. nn.linear. And here the projection is from latent dimension to 256 dimensions. And then after that there is a ReLU activation. And from 256 dimensions, we project again using fully connected layers into 784 dimensions, and after that we apply sigmoid activation. So that's it, the decoder, that's it. Here one thing we could do is we can say hidden dimension also is a variable, so hidden underscore dim equal to 256, and then use this variable here instead of 256, use the hidden dimension variable. That way, we don't have to keep changing. If I want to change the hidden dimension, I just need to change it in one place. So that also you can do. So that's the encoder and decoder, fairly straightforward. Now we can just define the forward pass. In forward pass, we first have x getting converted into latent. So latent is z. So z equal to self dot encoder, which we have defined above, of x. So x is the incoming input and we are encoding it, and then reconstructed is x reconstructed or x recon is equal to self dot decoder of z. So that is the reconstructed image, and now we can just return the reconstructed image. It will not be in an image format yet. It will be like a 784 dimensional vector, but we can plot it as an image using matplotlib. So we are now returning the reconstructed image. Okay, the pixels 784 pixels corresponding to reconstructed image. That's it. Autoencoder part is done. As I promised you, this is a fairly easy thing to code. I just ran it to make sure there is no syntax issue or anything. So far so good. Now we can just write, define the model. So defining the model loss. So auto or model equal to this class name autoencoder. So we are just initializing autoencoder class into this model object. Then criterion equal to, so this is again one of the other places where we use the nn which we had imported. So nn dot MSE loss, which is mean squared error loss. So we are not defining mean squared error from scratch. It's not needed. It's already predefined in nn. Then we say optimizer equal to Adam. So optim dot Adam, and the parameters that we want to optimize are the parameters in our model. So model dot parameters, and learning rate also we can define. Learning rate equal to, let's say 10 to the power of -3, 1e minus 3. This also will be another variable which we can change, and then I just run this block of code. So training loop has not started yet. That starts now. So we can say epochs equal to 5. So just running this for 5 epochs, and model dot train, and so model is set to train mode, not in eval mode. Then we say for epoch in range of epochs. So for loop for running the 5 epochs. Total loss, this is just to keep track of the loss. We initialize it as 0. Then we say for x comma dash in train underscore loader. So from the train loader we are taking data sets one by one, batches one by one. Now for this batch, what do we have to do? X equal to x dot view -1 comma 784 dot to device. So can you guess why this step is done in this case? So here what is being done is the x is a variable corresponding to our batches. So if batch size is 128, our size will look something like this. You have a grayscale image, so 128 is the batch size, comma 1, comma 28, comma 28, right? This is how the data input will look like. But then you can't pass this. When you are passing this, you want to convert this 28 by 28 by 1 into one single, one single 784 dimensional vector. So what you can do is you can sort of convert this into a format where this remains as 128 and this will become 28 by 28, which is 784. So the view function in Python, what it does is when you say -1, it will automatically calculate what the dimension over there should be. So then you could have asked, why not explicitly mention 128,74? Like I could have just explicitly said 128,784, right? Why did I not say that? Why did I say -1,784? The reason for that is, although we have mentioned the batch size to be 128, all the batches will be 128 except probably the last batch. Because if in my input data set there are, let's say 6,400 images, right? Let's say my batch size is, or let's say I have 6,399 images, okay? And let's say my batch size was 64. Then I will have 100 batches, right? So 100 multiplied by 64 is 6,400. In all the batches, I will have all the first 99 batches, I'll have 64 images. But in the last batch, there will be only 63 images. So we are not sure, although we mentioned the batch size, we are not sure if in every single batch there will be that many number of images or not. Sometimes the number of images in the last batch will be less depending on the total images available in the training data. So if in one of the batches, if this was like 126, then if I explicitly write it as 128, that's a problem. That's the reason why I keep it -1, so that Python will automatically calculate what the dimensionality here should be. Now this is what we can pass into our fully connected layers in nn.linear. So x.view of -1, 748. Actually, this is not 748, right? This is 784. -1, 784, dot to device. Then we say optimizer dot 0 grad. Again, what is this optimizer for 0 grad step? It simply says for each batch start with 0 gradient, and the previous gradients accumulated will not be considered, and then x reconstructed, x underscore recon equal to model of x. So model was autoencoder over here, model equal to autoencoder, and this class is ultimately returning x reconstructed. So you can say x reconstructed equal to whatever you get out of this model object belonging to autoencoder class. And then loss is equal to criterion, which we had defined. So criterion, and into this we pass our reconstructed image and the input x. Then we say loss dot backward. So we backward propagate based on the loss, and then we take in the Adam optimizer, we move ahead one step, and then the total loss underscore loss equal to total loss plus loss due to current iteration. And we can also define an average loss. Average underscore loss is equal to total underscore loss divided by length of train loader, which is the total number of batches. So this is the loss that is being accumulated batch after batch. At the starting it was 0, but as we move ahead through batches in this for loop, this total loss will keep on increasing. But if you want to know the batch wise average loss, the total loss need to be divided by the total number of batches. Total number of batches you can get from this train loader, length of the train loader. And then we just say print epoch. Then we need to mention the epoch number. So epoch plus 1. So epoch start from 0, I think. So 0th epoch I want to call as epoch number 1. And so 1 out of whatever is the total number of epochs. So total number of epochs is just epochs. So this will print like epoch 1 out of 2, 1 out of 5, 2 out of 5, etc. This epoch is the current epoch over here. Print this and comma loss. And for loss we can print the average loss. So average loss, and we mentioned the floating point precision, and that's it. I think I don't think we need to write anything in the training part. Now we can just run this. Let's see if there is any syntax error or something. Okay, mat1 and mat2 shapes cannot be multiplied. That is because hidden dimension 256. Let me just run this once more just to see if the error is reproduced. 128 multiplied by 256 and 784 multiplied by 32. Okay, latent dimension is mentioned to be 32. So we go from 784 to hidden dimension, then hidden dimension to latent dimension. So this is a mistake. So this should be hidden dimension to latent dimension. That is the encoder. In the decoder, you go from latent dimension to hidden dimension and hidden dimension to final dimension. So now let's try run all again. Yeah, now it seems to be working. Let's see if the loss is coming down. So loss, please note, it's a mean squared error loss, which is kind of interpretable. If mean squared error loss is 0, it means your reconstruction is exactly same. So the mean squared error after 5 epochs actually took only less than a minute to run. It's only like 0.01 after 5 epochs. We can run for more epochs if the reconstruction is really bad. So now we can set the model in evaluation mode, model.eval with torch.nograd. So we are not calculating gradients now. X comma dash equal to next of iter of train loader. So we are loading the data set from the training data itself just to see how the reconstruction looks like. And here actually we are just displaying the image that results from the decoder output. Okay, decoder has already trained, it has already been trained. So we are not doing any extra training or any work here. This is just for visualization, just for us humans to see. X equal to x dot view of -1 comma 784. This we had already done earlier in the earlier training loop, but here also we are doing the same. Then x underscore reconstruction is equal to model of x. So here we are just calling the model once again, but model is not set in training mode, it's set in evaluation mode, just to get the final output from the model, the 784 dimensional output. Then x equal to x dot CPU. This is just to set the variable x into CPU device. I think this step we can try skipping, it may throw an error, but we'll see. Then number of images that we want to display. Let's say it is 8 images that I want to display, n equal to 8. Then I can say plt.figure and fig size equal to 12,3. And then we can take images one by one. So for I in a range of n, so we have to plot these 8 images. plt.subplot 2, n, I plus 1. Then plt.imshow. This is where we display the actual image, x of I. So ith image from our input. So we have selected bunch of inputs from our, the batch. Then dot view. So we are viewing it as a 28,28 pixel image, and color map CMap equal to gray. Then plt dot axis off. We don't need to see the axis here. And then corresponding to this, we also have to plot the prediction. So plt dot subplot of 2, n, I plus 1 plus n. So in matplotlib, 2 means there are 2 rows, 1 row for the original images, second row for the reconstructed images, and there are n columns, and there will be total 8 columns, right? And I plus 1 is the index of the image, and I runs from 0 to 7. So I plus 1 will start from 1, it will go all the way till 8. So we will start by plotting in the column number 1, and a row will go from 1 to 8. And the reason why here the index is I plus 1 plus n is for the index I plus 1. So this is one entire plot. Okay, inside this loop, it's one entire plot. But inside this plot, we are creating subplots. And I plus 1 means it's the index of the actual image. I plus 1 plus n will be I plus 1 plus 8 will be the index of the corresponding reconstructed image. When I plot this, you will understand what this will look like. So plot.imshow x reconstructed, not x, just x recon of I dot view of 28 comma 28 and gray color map equal to gray, and again plt.axis off, and then we just need to say plt.show to display the plot. So let's run this to see what the output looks like. I think rest of the things are already ready. So okay, now this is the output. So these 8 images, so totally there are 8 plus 8, 16 images that are being plotted, but within each we are creating 2 subplots. So I will go from 1 to 8, but within each we are creating 2 subplots. So subplot number 1 in the first iteration is this 9. Subplot number 2 is this 9. The first one is the original image. Second one is the reconstructed image. This is the original image. This is the reconstructed image. And you can see that for some images, it's very confusing. So here 5 is reconstructed as a confusing 5 or 6. It's hard to say. And wherever there are some extra features like this, those extra features are not getting reconstructed, probably because you have a lot of inputs of images like this corresponding to 3. And if you really want the reconstructed image to be an exact match of the input, probably you'll have to train for more number of loops and maybe increase the latent dimension size. Right now it is 64. Now one more thing we can do is model dot eval. So we need to plot some things corresponding to every single dimension, right? So I have written a code here, which I don't think I have to write from scratch. This is just meant for plotting. So I'm having a model.eval so that all these latent variables I can store, all the values of the latent dimensions corresponding to every single input image I can store in a variable. And then I can plot like a nice scatter plot, which looks like this, right? So that's what we are going to do now. But this code is a little bit long. It's because I deliberately kept it with few conditions. So one condition was, if it's a one-dimensional latent space, I just want a histogram. If it's a 2D latent space, I need a 2D scatter plot. If it's a 3D latent space, I need a 3D rotatable scatter plot. If it's a higher dimensional space above 3 dimensions, I will convert it into a 2-dimensional space using principal component analysis. I'll find the two most important principal components, which can be easily done using library, and then I can plot it. I'm not going to go into the details of how principal component analysis works, but basically it will find the most important two axes through which the data shows the maximum variance. So this also I'm going to copy and paste here. Okay. So now in the 64-dimensional space, obviously we cannot directly plot. We have to convert it into principal components. So I'm just running the model once more in evaluation mode. And once it is done, I will show you the 2D principal component analysis PCA plot, how it looks like, how the 10 classes of the MNIST data will be distributed, etc. We can also run this once on fashion MNIST, but let's first run this on pure MNIST, just the handwritten digits. Okay, so this is now how my PCA principal component, two principal component axes looks like in 3D. You can see that there is very nice clustering happening. The 10 classes are clustered into almost distinct 10 clusters. Now let's start with one thing. Let's start with the embedding the latent dimension to be 1. What does this mean? If latent dimension is 1, it simply means you are representing the entire image in the latent dimension with just one dimension, with just one number. So of course it will be not so very good, because now with just one number you have to reconstruct your input image, and of course this should result in a lot of losses, right? So let's run this and see what kind of output we are getting. So now for the same number of epochs, the loss is 0.05 after 5 epochs. Earlier it was 0.01 or something. And these are my reconstructions. Clearly 0 is getting confused between 8 and 0. Same for 2. So most of these reconstructed images look almost the same. The variety is missing. And that is rightly so, because you are trying to reconstruct with just one latent, hidden variable. The distribution will be like a histogram. This is how it looks like. There is a lot of overlap. The digits that are not overlapping so much is 1 has a mean over here, and this blue is 0. So if you are trying to reconstruct 0 and 1, I hope the reconstruction will be good one. So let's see the reconstruction of 0. This is a 0. It is getting reconstructed like this. This is 0. It's getting reconstructed like this. But 1 is not getting. Let's run this one more time, so that hoping that, yeah, see, this is 1. 1 is getting reconstructed almost like this. So 1 and 0, there is good distinction between 1 and 0. Now let's look at the graph to see which data points the distinction is very less. I think the distinction between green and this blue, which is green is 2 and the light blue is 9. Distinction between 2 and 9 is very less. Here they are both occupying the same latent value, roughly around 2.5 or something. So if we are trying to reconstruct 2 or 9, or even this purple color is 4, 2, 4, 9, the reconstruction of those three numbers should not look very different. They might look alike. So 2, 4 and 9, let's see. So this is 2 looks like this. 9 looks like this. Okay, there seems to be difference. 4 is, there is no 4 here. We can run this one more time randomly. See, okay, 2 and 4 are there. See, The reconstruction of 2 and 4 looks exactly the same, very much the same. And 9 is not there here. Let me run this once more to see if 2, 4 and 9 I can get in one single. Here again I have a 9 and a 2. Look at this, the reconstruction of 9 and 2. So these are all 9s, 9, 9, 9, 2, 9. So these reconstructions of 2 and 9s are all looking the same. I'm sure there are more numbers whose histogram is falling such that the latent value, mean latent value is close to each other. So all these numbers actually have mean latent value that are very close to each other, except 1 and 0. So 1 and 0 are at two extremes, but all the other digits may look kind of similar. So this is with a 1D latent space. What if we change it to 2D? Can we have a lesser loss? So right now just take a look at the loss for same number of epochs, 0.05. If I use a 2D latent space, what can my loss become after 5 epochs? Let's come back after these epochs are done. So this is with 2D, the loss has reduced to 0.046, which is slightly lower than the previous case. And the reconstruction seemed to be marginally better. It's hard to say whether it is incredibly better. It's marginally better for sure. And when we run this again and again, you see the reconstruction is kind of resembling. There is a lot of variety in reconstruction first of all, and they are resembling the original image, right? Let's look at the scatter plot, 2D scatter plot. Seems like, yeah, I have to run this once. Actually, I should run both of this. I need to first get the latents here stored, and then I have to run the plot once. So this is the 2D scatter plot, and you can see that there is a huge difference between plots of, let's say, digit 0 and digit 1. So this is 1 and this is 0. They are farthest apart. So their plots will have good distinction, but there is a lot of overlap between some of the other digits. But in general, you can see a lot of clusters are there, right? Which means that in the latent space, the regions that you are occupying are kind of distinct. One more thing that I can do here is, in this plot, I'm not sure if we are only plotting positive numbers. I think we are only plotting positive numbers, which is why there is an abrupt cut here. But I'm not 100% sure if we are also converting to negative numbers in the latent space. We are applying a sigmoid at the end, which is between 0 and 1. So I don't think we can expect to have negative numbers at the output. Okay, so makes sense. So this is for two-dimensional latent space. We already saw the 64-dimensional latent space. Now what we are going to see is looking at the 3D latent space. So 3D hopefully will be even better. So here the loss was 0.046. For 1D space it was 0.05. For 64D it was 0.01. For 3D hopefully it will be somewhere in between. So for 3D, the execution is done, and I don't think the loss significantly reduced. It's 0.041, lesser than before, and reconstructions are again slightly more better, but I cannot say that for sure. I like looking at these 8 images. I can't say for sure reconstructions of all images are really good. It's okay. And here is the 3D space, latent space. You can see that again there are clusters, but since it's in 3D, it's hard to say which ones are overlapping, because in the third dimension maybe the overlap is less, but this is how it looks like. The best thing we can do is increase the number of dimensions in the latent space to, let's say, something like 128. So let's keep this as 128 and let's see how good the reconstruction is. I will also do one thing, which is in epochs I can increase to 20 to see the best reconstruction. And then let's pick a random latent vector which is not connected to any reference image, a random latent vector, and see how the reconstruction looks like. Okay, so I'm going to run this 20 epochs. So the execution is finished and the loss is very small, 0.003. And when you look at the reconstruction, they look almost same as the original. So the top row is the original, bottom row is the reconstruction, really good. We can also plot the principal component, 2 principal component axes. That is what you're seeing here. There are clusters. You can see some overlap, but looking at the quality of reconstruction, which you can run again and again, you can assume that, you know, the space is large enough to provide enough variability for any kind of input image. But now here is the other interesting thing to do. If we randomly pick a latent vector from the latent space, will that vector also result in a good reconstruction? As we discussed earlier in the theory part, it probably does not, right? So here is a random latent vector. So here what we are doing is we are picking a random vector from the latent space and then passing it through decoder and using that decoder output to display the resulting image. Okay, so this I can run any number of times and look at the sort of images resulting from my 128 dimensional latent space if I am randomly sampling vectors from the latent space. These are utter useless images, right? They are complete random looking reconstructions. This is the number one issue with autoencoder if you are using it as a image generation model. It is not at all a good image generation model. It is good to reconstruct the image provided the latent vector resulted from an actual input image. On the other hand, if you are creating a random vector whose dimensionality is in the latent dimension, latent space, the resulting generated output image, which is from the model decoder, will look something like this. So you can run this any number of times in the hope that if the latent vector is close to one of the vectors corresponding to an actual reference image, you may get a good, you know, resulting reconstruction. But you can run this again and again. It's very difficult to get a very good reconstruction. So this is the problem with autoencoder, and this was one of the reasons, primary reasons why variational autoencoder was introduced. We'll discuss about variational autoencoder in a separate video, but I hope you understand the value of autoencoder as a really nice compression mechanism. If you have a trained autoencoder, the encoder part of the autoencoder alone can be used for constructing good compressed versions of your input data. And decoder as such, if you are just using decoder part of the autoencoder, it is not that useful because the reconstruction has meaning only if the input that goes into the decoder is corresponding to some actual image. But if the input which goes into the decoder is a random data point from your latent space, your reconstruction will have no meaning. But your encoder alone, a trained autoencoder, you can use just to take apart the encoder, and that encoder can be used to encode whatever new images you have to input. So if it's an MNIST image, you can use that to be input into as an input into the encoder to produce a very good compression in the latent space. Now, before we wind up, one last thing we can do is do the same for fashion MNIST. So here we say fashion MNIST, and number of epochs we can reduce actually. Let's keep it 5. And let's not have, I don't want to see the latent space or anything. So let's just comment out this part of the code. This is just to see how good the reconstruction look like, right? So just 5 epochs, 128 dimensional space. This also we could reduce to 32 or something like this, just so that the code runs a little bit faster. And oh, there is some error, fashion MNIST. I think fashion MNIST is also 28 by 28 MNIST data set pixels. Yeah, so this is also 28 by 28, exactly like MNIST, but except these are these clothing apparels. There are these 10 classes, t-shirt, trouser, all these, and different varieties of that. So now let's see. So if you remember the loss for 64 dimensions, right now we have defined the actually this is 32. For 64 dimensions, the loss was 0.01 after 5 epochs. Here also it's almost reducing it to that level. And hopefully the reconstruction will look very good. Let's see in a minute. So the execution has finished, and this is the reconstruction. So shoe, some full sleeve shirt, sneakers, all of it's getting reconstructed in a very nice way, but a lot of details are missing. So this shirt actually has this looks like a female upper body wear, and it looks like a there are stripes, but those stripes are not getting reconstructed. And if I run just this block once again, it will reconstruct and construct another set of these clothing apparels. So you can see that it's blurry, but reconstruction is working just like MNIST. So I recommend you to play with the parameters, basically the latent dimension, try one-dimensional data, also try a larger number of dimensions and see how the reconstruction looks like. And just feel free to comment what was your results from your experiments. So thank you so much. That's a good place and time to wind up today's lecture. I hope you understand autoencoder, how it works and for what it can be used and for what it cannot be used, and why do we say that it's not a great generative AI model, because the reconstruction is not the greatest. In next lecture, we will discuss about variational autoencoder, which is significantly better than autoencoder at generalizing the latent space representation capability. So at that time, you will understand why aspects of probability and Gaussian distribution has to be introduced into the latent space, because right now, even if you pick a representative point right next to, even if you pick a point right next to a representative reference point, the construction, which is the reconstructed image, is very bad, but that need not be the case. If you are representing your latent space as a probability distribution, you can sample from nearby your mean and still end up getting a really good reconstruction. So we will discuss all of that in the variational autoencoder lecture. So take care until then. Thank you so much. See you soon. Bye.